In this video, we're going to talk about how to test the claim about a population proportion, and this is testing the claim for one proportion. We have another test for testing the claim for two proportions to compare, and we'll talk about that later. So the requirements, we got to have a simple random sample. N times P times 1 minus P has to be greater than or equal to 10, and the sampled values have to be independent of each other. Our test statistic, here's our formula for a test statistic. It's going to be P hat minus our P naught, the value that we're testing, divided by P naught times 1 minus P naught divided by N. And we're taking the square root of all of that. So I'll show you how to do one by hand. We'll talk about the two different ways of testing, the critical value method and the p-value method, and then I'll show you how to use technology. So what are my steps to perform a hypothesis test in general? You always got to make sure that your requirements are met. You got to find the null and alternative hypothesis. You got to figure out what your alpha value is. You got to find the test statistic. You got to figure out, is it left, right, or two-tailed? Because remember, that's tied to alpha. And then you just compare P to alpha. P is greater than alpha, you fail to reject. P is less than alpha, you reject. And then we're going to state our conclusion, and you've got that nice chart to help you state the conclusion. If we're using the traditional method, you still got to make sure requirements are met. We're going to find the critical value. We're not using StatCrunch. We are using SALT. We're going to find that test statistic and we're going to determine the outcome. Whether that test statistic falls in that critical region or not will tell us whether we reject or fail to reject and then state our conclusion. So let's look at an example. In a presidential election, we had 308 out of 611 voters surveyed, so they voted for the candidate who won. Use a 0.01 significance level to test the claim that among all voters, the percentage who believe they voted for the winning candidate is equal to 43%. Let's see if I can. And that was the actual percentage who voted for the winning candidate. So that's what we're testing. So let's write down what we know. We know alpha is 0.01. We know p hat is 308 out of 611. We got our null and our alternative hypotheses. So p is equal to 0.43. That's our null. And that's what they gave us. So the alternative is not equal to. Since they gave us the null, the alternative is not equal to. That tells us this is a two-tailed test. And we know n is 611. So let's figure out what our test statistic's going to be. Z is going to be equal to p hat minus p, or p naught, however you want to think about it, divided by square root of p1 minus p over n. So p hat is the 308 out of 611. Our p is what we're testing, 0.43. We're going to divide by the square root of 0.43 times 1 minus 0.43 all over n, which is 611. Now, when we type this in the calculator, we've got to be really careful. So if you need to do it bit by bit, you can do it bit by bit. That's fine. I'm going to do that off screen. And when I do that, I get about 3.70. So there's my test statistic. So if we're doing this the traditional way, the traditional way compares the test statistic in the critical region. So our alpha is 0.01, and since this is a two-tailed test, we've got to split that 0.01 into both tails. So I'm going to have 0.005 here and 0.005 here. And this is where I would go to salt, and I would type in 0.005. I'm getting negative 2.58. So this is negative 2.58. That means this has to be a positive 2.58. And our test statistic was 3.7. So we're going to ask, where does that test statistic live? Where 3.7 is over here. Do you see how that's in that rejection zone? A rejection zone is tied to our alpha value. And since the test statistic falls in there, then we would reject H naught. So that's your traditional way that you would look at that. Now let's look at the p-value method. You're going to get the same conclusion either way. P-value method looks at the probability of being beyond the test statistic. So here's my test statistic at 3.7. This is a two-tailed test, which means I need to consider that left-hand side also. I need to know what that number is. I'm looking for that p-value. So that's my right tail. 3.7, and it's going to be pretty small, 0.00011. I'll go 4 decimal places, 0.0001, which means this has to be the same. So the p-value is this plus this, which is 0.0002. And since that region combined is less than this region combined, p is less than alpha. So 0.002 is less than 0.01. Then we would reject. So you're going to get the same answer either way. I like the p-value method. If we were doing this using our statistics software, inferential statistics, we're doing a one sample proportion. The number of successes was 308. The number of trials we had, that's your N, 611. And this is a hypothesis test. The hypothesized proportion was 0.43. Now it's coming from what we're testing here, and this is a not equal to. We're going to generate those results. So it gives me my p hat, which is this divided by that. And then here's your p-value, no, just kidding. Here's your p-value, 0.0002. So then we would compare p less than alpha, we reject. There's your test statistic that we computed by hand. So you see, it's giving you the same information. So now that we have that, we've got to figure out what are we going to do for that final conclusion. So which of these are we going to use? We want to test the claim that the percentage of people who believe they voted for the winning candidate is equal to 43%. So the original claim contains inequality, and we ended up rejecting. So we would say there is sufficient evidence to warrant the rejection of the claim. And then we would just insert the claim. There's sufficient evidence to warrant rejection of the claim that the percentage who believe they voted for the winning candidate is equal to 43%. Okay, let's look at another one. And this is where you may want to pause the video, try it on your own, and then come back and check your answer. Clinical trials involve treating flu patients with Tamiflu. Among 724 patients treated with Tamiflu, 72 experienced nausea as an adverse reaction. We want to use a 0.05 significance level to test the claim that the rate of nausea is greater than the 6% rate experienced by flu patients given a placebo. So let's write down everything we know. We know alpha is 0.05. Our p hat is going to be 72 out of 724. Our h naught is looking at the 6%. We're testing the claim that is greater than 6%, which tells us this is a right-tailed test. So let's find our p-value. We're going to go to SALT and we're going to type in everything we know. This is a one sample proportion. Number of successes, there are 72 who had nausea out of the 724. The hypothesized proportion is 6%, and we are looking at a greater than. And we're going to generate those results. So our p-value is super small here. Our test statistic is 4.47. I think 1, 2, 3, 4, 5 zeros in front of that 4. In this case, p is definitely less than alpha, which means we're going to reject h naught. So how do we phrase this? So let's go back to our chart. The original claim does not have an equality. It used the word greater than, and we did reject h naught. So we would start by saying there is sufficient evidence to support the claim that. And notice we're supporting that alternative hypothesis. So I got another example. You may want to take a minute, pause the video, try it, and then come back and check your answer. So in this one, we have a study of 420,095 Danish cell phone users. 135 developed cancer of the brain or nervous system. We want to test the claim that cell phone use. Well, see if I can get it to highlight. Test the claim that cell phone users develop cancer of the brain or nervous system at a rate that is different from the rate of 0.034% for people who do not use cell phones. And we are going to use a really small significance level, 0.005. So we've got alpha as 0.005. We're talking about cancer. We want to be really careful with that. That's why we're using such a small significance level. We want to leave very little room for error. Remember, this is the alpha is tied to your errors. Our p hat value is 135 out of 420,095. H naught Remember, we're turning this into a decimal, so we're going to move that decimal 2 places to the left. We're saying different from, which means not equal to. So let's figure out what our p-value is going to be. Go in here. Number of successes was 135. Number of trials was 420.95. Our hypothesized proportion is 0.00034. And we are looking at not equal to. So our p-value here is 0.5122. And p is definitely greater than alpha. So we are going to fail to reject. So let's figure out how we're going to word that final conclusion. The original claim said different from, and different from does not have an equality. An equality would have to say equal to, okay, or greater than or equal to, or less than or equal to. It would have to have an equal to statement in it. So this does not, because it says different from, and we fail to reject. So we would say there is not sufficient evidence to support the claim that, and then insert claim. Okay, let's look at another one. Take a minute, pause the video, try it, come back, check your answer. Trials in the experiment with a polygraph graph include 98 results, 24 cases of wrong results, and 74 cases of correct. We want to use a 0.05 significance level to test the claim that polygraph results are correct less than 80% of the time. So let's talk about everything we know. We know alpha is 0.05, p hat. And since we're testing this, how correct they are, we're going to end up using that 74. So 74 correct out of 98, that's correct. So that's my successes and how many trials I had. And figure out our hypotheses, testing the claim about a proportion, correct less than 80% of the time. So let's type everything in. We're going to go to salt. Number of successes is 74. Number of trials is 98. Hypothesized proportion is 80%, and this is a less than, which means a left-tailed test. Test statistic is negative, and our p-value is 0.1332. Okay, in this case, our p is greater than alpha, so we are going to fail to reject. So how are we going to phrase that? We do not have inequality in the original claim, and we fail to reject. There is not sufficient evidence to support the claim. And we're going to look at one more. Out of 123 people, 62 enjoy cleaning. Test a claim that no more than 30% of people enjoy cleaning. And we are going to use a 0.05 significance level. So let's talk about what we have. We have the claim, which is no more than 30% of people enjoy cleaning. We have p hat, 62 successes out of the 123. Alpha is 0.05. But this wording is a little bit different. Test the claim that no more than is actually an equality statement. So this is actually P is less than or equal to 30%. So what would the alternative look like? Well, the alternative has to be the opposite, which is going to be greater than 30%. But we're not used to seeing things this way. Back when I took statistics, we did write the null hypothesis that way. Now, most textbooks will have you write it as an equal to statement. And then the alternative is still greater than 30. So this is actually a right-tailed test. So we're going to type in everything we know. We're going to go to salt. We had 62 successes out of 123 trials. Testing the claim about 30%. And this is actually a greater than problem. So our p-value ends up being 0.00001, super small. P is less than alpha, we're going to reject. So we have to be careful how we phrase this. The original claim has an equality. And then we're going to reject H naught. So original claim has an equality, and we're going to reject H naught. This is how we're going to phrase it. There is sufficient evidence to warrant rejection of the claim. That no more than 30% of people enjoy cleaning. So there's how we test a claim about a proportion.